confidence intervals for regression lines. Recall that a regression line is a line that describes a relationship between the explanatory variable x and the response variable y. The least squares regression line formula is y hat equals a plus bx, where a is the y-intercept and b is the slope. The slope of a regression line can help determine if a relationship exists between two variables. When the slope of a regression line is 0, no relationship exists. The assumptions for regression inference are: if we hold x fixed and take many observations of y, the normal pattern will eventually appear in a stem plot or histogram. Repeated values of y are independent of each other. The mean response of y has a straight line relationship with x. In other words, mu sub y is equal to alpha plus beta x. The slope beta and the y-intercept alpha are unknown parameters that we're going to make inferences about. The standard deviation sigma of y is the same for all values of x and is unknown in our situations. First, we're going to begin with confidence intervals about the slope for regression lines. The confidence interval for the slope of a regression line, note that we're going to be given some sample data and we're going to make an inference about the slope if we were given the population data. So we're going to take our sample data and find the y-intercept b. Then we're going to add and subtract our margin of error, which is found by our t star, our critical value t, which has n-2 degrees of freedom, times our standard error of the slope. Now, our standard error of the slope needs two steps to calculate. First, we need to find this value s, which is the sum of all of our y's minus y hats, in other words, our residuals, squared, divided by n-2 square rooted. And we take that value and we're going to divide it by the square root of the sums of x minus the mean value of x squared. We're going to let the calculator do this work for us. So in this example, we want to know how well golfer scores on the first round can predict their scores for the second. Here we have recorded 12 rounds, and we're trying to find out if the scores in round 1 can predict round 2. So round 1 would be our x values, and round 2 will be the y values. We want the least squares regression line for the data, and we want to report on our r and r squared, and then we're going to compute the 90% confidence interval for the slope of the regression line. So we're going to begin by entering our x and y data into L1 and L2 in our calculator. Remember, we're going to go stat edit, and we enter those data. So L1 is my x values, L2 represents my y values. Now first, let's get our least squares regression line, our r and our r squared. So I'm going to quit out of this mode, and I'm going to do stat, calc, and we're going to do our linear regression a plus bx, which is 8. Our x list is in L1, our y list is in L2. We ignore the frequency list, and we're going to store our regression equation in, sorry, I didn't want to do the second there. Let's try that again. Stat, calc, 8. And we're going to store our regression equation in variables, y variables, hit enter for function and choose y1. Make sure your diagnostics are on so you can get all these values. So I've pasted our calculator values right here, and this makes our regression equation equal to 26.33 plus 0.6877x. There's our r squared and our r. You can see that we have a positive linear association, although it's really not that strong. All right, so now we're going to create our confidence interval for the slope. Once again, our formula is our slope from our data that we're given plus or minus our t star critical value times the standard error of the slope. Let's get our t star critical value. Remember, this is a 90% confidence interval. So we're going to do inverse t or qt, either one with the same values. Now recall that with a confidence interval, we're trying to find the value between two, so we don't use these two tails. So if in here is 90%, we have 10% in each tail total, which gives us 5% here, 5% there. So we're going to do inverse t of 0.95, or rather 0.9 times 1 minus 0.9 over 2. And our degrees of freedom, a little different from our other tests, is n minus 2. We have 12 pieces of data, so our degrees of freedom is 10. This will give us a t-star value of 1.812. Now our standard error. Now to first get the standard error, we need to get the value s. Now s was the square root of the sum of our residuals, y minus y hat, squared divided by n minus 2. Now we can do this within our list of the calculator. So what we're going to do is first we're going to fill up L3 with our residual squareds, and then we're going to add them up. So let's go back to our lists. We're going to go to L3 and hit enter so that we can put in a formula for the entire line. So we're going to do our y values minus our predicted y values, which are in y1, and those predicted y's need our x's plugged in, and we're going to square that. So this is y minus y hat with our x's plugged in squared. Now I'm going to quit, and I'm going to go to list, second stat, go over to math, and find the sum of those values. Now we take that sum and we're going to divide it by our n minus 2, which is 10. And then we're going to square root that answer. So 5.974 is our S value. Now our standard error for the slope is our S divided by the square root of the sum of our x minus our mean x squared. So our numerator will be 5.974. In the denominator, again, we're going to let the calculator handle this. So let's clear this. We need to find the mean value for x. X was stored in L1. So we're going to go to list, over to math, and tell it to get the mean, that's 3, of L1. That's 89.6 repeating. Now I'm going to go back to my lists, and in L4, each one's going to be my x value minus this mean x squared. And that's what we need to add up, x minus x bar squared. So I'm going to fill it up. All of those are my x minus x bars. Quit, go back to list, math, and sum those values that we just put in L4 up. So this is the sum of all those. So what we have is the square root of 674.667 in there. So when I divide this out, I get a standard error of approximately 0.23. So our confidence interval will be our slope, oops, that's our A, sorry, our slope plus or minus our T star times the standard error. And that gives us the confidence interval from 0.27 approximately to 1.105. Now let's look at an example where we have computer output. So this is computer output for a regression line, and the way it's given to us, the word constant tells me where my intercept is, and the coefficient of my variable for my x is my slope. So my equation of my regression line for this problem can be easily read off as 74.8 plus 19.718 times x. Now here we want the 95% confidence interval. So we need our T star, our critical value T, and we're going to need our standard error for the slope. Our T star for the 95% confidence interval, we'll do inverse T or QT of 0.95 plus 1 minus 0.95 over 2, and we use n minus 1 degrees of freedom. Our n is the 71 houses, so our degrees, 73 houses, so our degrees of freedom is 71. This gives us 1.99 for our critical value. Next, we need our standard error for the slope. That's read from the chart. Look at the standard deviation, look at the slope, and that's our value. So our confidence interval will be our slope plus or minus our T star times the standard error for the slope, which gives us the interval 14.47 to 24.96. So we are 95% confident that the true slope for the appraised value of the number of rooms of houses in South Springs, Texas is between 14.47 and 24.96.